Algebra 2, Chapter 5, Section 1, Linear Functions. A linear function is a function whose rule can be written in this form. F of t is b plus m times t, for constants b and m. And the constants b and m are parameters for the linear function family. We call these functions linear because the shape of the graph of any of these functions will be a straight line. B represents the initial value, f of 0, of the function. It's what we get out when we put in 0, because m times 0 is 0. On the graph, this is called the y-intercept, if we're graphing x and y, or the vertical intercept. M represents the rate of change. On a graph, this is called the slope, and the slope can be thought of as the rise over the run. A positive slope, the graph rises as you go from left to right. A negative slope, it falls. Your rise is negative. Like direct proportionality, the rate of change m is the same on all intervals. So you have a constant rate of change. A constant rate of change. Unlike direct proportionality, the line of the graph does not have to go through the origin. It can go on. It goes wherever this y-intercept is, or the vertical intercept. So you can see, as an aside, that if the vertical intercept is 0, you have a direct proportionality. It's the same thing. It's equivalent to a direct proportionality if the y-intercept is 0. So let's think about and learn about these linear functions using a couple examples. The population of a town, t years after its founding, is given by this linear function, 30,000 plus 2,000 t. What is the town's population when it is founded? In other words, what is the output when the input is 0? And again, we already know this just from this form of the function. This is the initial value, 30,000. This was our b, 30,000. What is the population of the town 1 year after being founded? So what's p of 1? Well, it'll be 30,000 plus 2,000, 32,000. By how much does the population increase every year? Well, each year we have 2,000 more people. That's our rate. Sketch the graph of the population over time. So we could use graph paper, but since it says sketch, we'll just draw best we can some straight lines for our axes. Doesn't make any sense for the population to be negative or for time to be negative. So we're only going to graph the first quadrant. Here's time. Here's population, p of t, time t. So when the town is founded, there are 30,000 people. 30,000. Okay. Let's say 10 years after it's founded, population will have gone up by 10 times 2,000, which is 20,000 people, to 50,000. And we might pick a different color to draw the actual line. So the line will come up here and slope through this point and just keep going. We could figure out, for instance, the population at any particular year by thinking of the slope and looking at the graph. Identify the vertical intercept and slope and graph the following functions. A, f of x is 100 plus 25x. Okay, so here we have the vertical intercept b is 100 for part A. And the slope, m, is 25. It's fairly easy to identify from this function. So we need to graph 125. Let's make a new page here. And instead of using paper, let's make this page be a graph page. Okay, so we needed to graph, let's flip back, 125. So the y-intercept was 100, and the slope was 25. So here's our graph paper. We'll make our origin here. Draw our lines. So when we're doing a more detailed graph, let's be careful about how we do it. Use graph paper if you have it, or a ruler. It also makes great straight lines. I don't have a ruler, unfortunately, so my lines are wobbly. But we have the graph paper to go off of to help us get corrected. So let's make some axes. Let's flip back and look at what we should label them with. X is the input, and the output is f of x. So x is the input, the output is f of x. Now we know that when the input is 0, the output's 100, and then our slope is 25. So let's make every one of these boxes worth 25. So we'll put 100 on the output, and then every one of these boxes will just represent 1 unit of time, or 1 unit of x, sorry. So 1, 2, 3, and so on, minus 1. And we don't have to label all of them, just a few, so we know what our scale is. So we have 100, we might go ahead and label 50, and 150. And so the function was 100 plus 25x. So our y-intercept was 100. And our slope is 25, so we go over 1 and up 25. And since our units are here in 25s, it'll just be over and up 1 for each point. And of course the graph keeps going in every direction. So let's start here, go this way, remembering our rise over our run. Draw an arrow representing that it keeps going. Doesn't stop just because it's past our viewing window. And that's what a graph of this function would look like. What about part B? G of t is 6 minus 0.5t. Here the b is 6 and the m is minus 0.5. So let's make another graph piece of paper here. Add some graph paper. So we have to go ahead and put our axes down again. Make this our origin. Go up and then go down. Maybe we should have written down our problem first. It's g of t is 6 minus 0.5. So g of t is 6 minus 0.5t. So this is t, and this is g of t. Our y-intercept will be 6, so let's make each of these worth 2. So this will be 6, 4, 2. And our slope is negative 0.5. So we'll have a rise of negative 0.5 for a run of 1. Now we could think of negative 0.5 as a fraction. It's 1/2. So we'll rise 1, negative 1, for a run of 2. So let's make each of these worth just 1 unit of time. 2, 4, 6. And maybe we don't want to make these different. Let's just make everything worth 1. 1, 2, 3, 4, 5, 6. 6, 3, 1, 2, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you don't have to label all these, but I'm going to this time. So our y-intercept is 6 here. And we have a rise of negative 1, which is a fall. So we'll fall down. So we have a rise of negative 1 and a run of 2. So each time we'll go down 1 and over 2. Down 1, over 2. Okay? So our graph will look like down 1 and over 2. C, h of z is 3 times the quantity 1 minus 2z. So here we need to use the distributive law to make this into a linear function in the form that we know of, which is the form with the b and the m. So we have a b of 3 and an m of negative 2/3. So we have h of z. Let's make a new page. So we have h of z is 3 minus, we'll just double check to make sure we get it right, 2/3 z. Find an origin on our graph paper. Draw some axes. Try not to make them too squiggly, but sometimes that happens. Let's try and make it a little straighter. Okay, so we have z as our input, and h of z is our output. Our y-intercept, or our vertical intercept, is, since it's not really called y here, is 3. And we have a rise of negative 2 and a run of 3. So go quick and just label a few points. So we rise negative 2 and run 3. So our first point will be here. Then we rise negative 2 and run 3. Our next point will be here. And going backwards, we rise negative 2, run 3. Drawing our line, we have a graph. Another example, worldwide consumption of soda rose at roughly the rate of 150 billion liters from 1995 to 179 billion liters in 2000. First, A, find a linear function that estimates the quantity of soda consumed, S, in billions of liters, T years after 1995. So the output will be the S, the billions of liters, and the input will be T. So we'll have S of T, and now we need to find our linear function. So to do this, we need to use the points that we've been given. We know that we have, at the beginning, 150 billion liters. But we have to add some slope times t. We don't know the slope. We weren't given the slope. We were given, in 2000, there were 179. So we can write an equation from the second thing we were given. We were told if we put in the year 2000, which is 5 years after 1995, so t would be 5, we get out 179 billion liters. So we can use this to write an equation from the first statement. So putting in for the rule, we have 179, which is S of 5. Just reversing this. And S of 5 is, putting in 5 for t, 150 plus m times 5. Okay, so we have an equation. 179 is 150 plus 5m. Subtracting 150 gives us 29 is 5m. So m is 5/29. Sorry, we got that backwards. Let's not go fast. I think mess up. M is 29 divided by 5, which 30 divided by 5 would be 6. So this will be 5.8. And our slope is in the output units, which is billions of liters. Billions of liters, billion liters, over the input unit, which is the years. So billions of liters per year. 5.8 billions of liters per year. More soda is consumed each year. Okay, so now we can answer part B. Oh, first we need to finish. We have to find a linear function. So we need to put in m as 5.8. Here's our linear function. B. Give the units, which I already started doing, in practical interpretation of the slope and the vertical intercept. So starting with the vertical intercept first, its units are plain. It's 150 billion liters. So that's the vertical intercept. The slope, as I was explaining, must be an output over input, because it's the output is the rise part. It's the rise over the run. So think of that, rise over run, the output over the input. So you have 5.8 billion liters, that's the units of the output, over the units of the input, which is years. So billions of liters per year. 5.8 billions of liters per year. That's the answer to part B.